Hi everyone. So our previous video was supposed to be the final video of EMFT, but now this will be the final video. In this video, what we need to study? We need to study the polarization at media interface. So what we actually need to study is that, let's just say this is my boundary, or you can say media interface. So a wave is coming, it is striking here. This is the incident wave, this will be the reflected wave, and this will be the transmitted wave. We will study normal incidence as well, we will study oblique incidence as well. Now the question would be, let's just say my incident wave is linearly polarized. So what will be the nature of my reflected wave and what will be the nature of my transmitted wave? Whether the reflected wave will be linearly polarized, circularly polarized, or it will be elliptically polarized, or transmitted wave will be of what nature? Similarly, the same case in incident, so in the same case in oblique incidence as well. And we will see two kind of reflection there: normal reflection and total internal reflection. So all these kind of topics we are going to discuss. But before that, let's revisit polarization. Okay, what we are revisiting? We are revisiting polarization. So we have already studied it, but just watch this video again, because here I'm gonna tell you one trick as well. So this is the first question. You need to tell what kind of polarization is there. So what is the phase shift? You can see the phase shift is pi by 2. What is the magnitude? Magnitude are equal. If magnitude are equal, phase shift is pi by 2. What is the answer? Circular polarization. But right hand or left hand? So till now, how we used to do it? Till now, whatever that I have taught, till now, how we used to find whether it is right hand circularly polarized or left hand circularly polarized. So what we used to do is that we used to write its time domain form. That would be sine cos omega t minus beta z. But since the wave is propagating in z direction, so I will sit on z equals to 0 plane. So I will put z equals to 0 here. And what do you mean by z equals to 0 plane? Z equals to 0 plane means xy plane. So we used to make xy plane. What we used to do is that we used to make xy plane, and then we used to sit on this xy plane, which is z equals to 0 plane. So let's just say this is your x, this is your y, and where would be my z? Z would be coming towards me. And then I used to write down the direction of propagation, that is plus z only. So direction of propagation is this. So I used to write down the time domain form, and this pi by 2 phase will go inside. So here I used to write down cos omega t minus beta z. So I have written time harmonic vector field form. This is how this is ax cap and this is ay cap. Then what we used to do, we used to put z equals to 0. Here we used to put z equals to 0. So what is the scene? Cos omega t ax cap plus e naught cos omega t plus pi by 2. Then what we used to do, we used to vary the time, that I will put t equals to 0 first. So if I put t equals to 0, what I am getting? My equivalent e naught in x direction is, my equivalent e field in x direction is e naught. My equivalent E field in y direction is not there, that is 0. Then I used to put t equals to t by 8, or I can put t equals to t by 4 as well. If I put t equals to t by 4, then this component will be 0 and this component will be minus E naught. That means if this is your y, this would be your minus y. That means my equivalent vector is minus E naught ay cap. So here is my E naught, previously here is my E naught. Now I know that it is circularly polarized, but the direction will be like this. So that the direction is like this. The direction is clockwise. So what is my direction of propagation? That is coming towards me. So what hand I need to use? Left hand circularly polarized, because my finger should rotate in the direction of circle and thumb should be pointing towards. So my finger should rotate in the direction of circle and thumb should be pointing towards the direction of propagation. So left hand circularly polarized. So this is how we used to do it. But now I am telling you a trick, that how quickly you can do it. Here it will take some time, right? But for quickly doing it, what we need to see, who is leading here? Y is leading here. So I am marking this as a lead. Why Y is leading? Because Y is having a phase of plus pi by 2. So here Y is leading, and who is lagging here? X is lagging. So now you need to move your hand, listen to it very carefully. Now you need to move your fingers from lead to lag such that your thumb is pointing towards the direction of propagation. First I will make the axis, I will mark lead and lag. Now I will move my hand such that I will move my fingers such that my fingers is moving from lead to lag and my thumb is pointing towards the direction of propagation. So my fingers is moving from lead to lag and thumb is pointing towards the direction of propagation. That means left hand circularly polarized. Although this part I have already recorded, but somehow this part got deleted. Like basically this complete video has been already recorded, but somehow this part of the video was deleted, so I have to record it again. So I'm recording it again. But don't feel like that I will miss any point. I will certainly tell all the points. Now from here to here, what we are doing? Here E naught, everything is same. Even here Y is leading, here also Y is leading. Here Y component was leading. Here the component of E field is two E field component are there. One E field component is dancing in X direction, one E field component is dancing in Y direction. Right? Here also E field component is dancing in X direction, Y direction. Magnitude are also same. Just the point is that, and here also Y is leading, here also Y is leading. Just the point is that I have changed the direction of propagation. Here the direction of propagation was plus Z, here the direction of propagation is minus Z. So can I write down with respect to question 1, what is the change here? Direction of propagation inverted. Direction of propagation inverted means just the opposite. Direction of propagation inverted. Now we already know it is circularly polarized. So whether it is left hand or right hand, let's check that out. It is left hand or right hand. So this is my Y, this is my X. Who is at lead? Y is at lead. Y is at lead. Who is at lag? X is at lag. Where will my Z? X cross Y. Z will be towards me. But what is my direction of propagation? My direction of propagation is going inside the plane, because my direction of propagation is in minus Z. You can see here the direction of propagation is in minus Z, and here the direction of propagation was in plus Z. And this was at lead. Here also this is at lead. Say yes or no. Well and good. So now what I need to do, move your hand from lead to lag. Move your hand from lead to lag such that your thumb should be pointing towards the direction of propagation. Where is my direction of propagation? Going inside. Moving my hand from lead to lag. Lead to lag, thumb is pointing towards the direction of propagation. Lead to lag, thumb is pointing towards the direction of propagation. Right hand circularly polarized. So a very important conclusion we made here, that if I invert the direction of propagation, keeping all other things same, direction of propagation inverted and phase difference not disturbed. I did not disturb the phase difference. So I kept the direction of propagation, I inverted the direction of propagation, but I kept the phase difference same. So only by one change, left hand circularly polarized became right hand circularly polarized. Are you agreeing to this point? Yes. Now with respect to question 1, what we are going to do is that we will take the direction of propagation to be plus Z only, but we will change the phase now. So what we are doing here, what is the direction of propagation? That is plus Z only. But this guy was at lead. Now this guy is at lead. One change I am doing. Here one change was direction of propagation. Here the change is direction of propagation. No. Here the change is lead has become lag and lag has become lead. So again I will make XY axis. Who is at lead? This guy. Why I am making like this? This guy is at lead and this guy is at lag. Where will be your Z? X cross Y should give me Z. Z will be going outward. And what is your direction of propagation? Direction of propagation is also coming outward. So we need to move our hand from lead to lag such that my thumb should be pointing towards the direction of propagation. Move your hand from lead to lag such that the thumb is showing the direction of propagation. From lead to lag and thumb is showing the direction of propagation. So lead to lag, thumb is showing the direction of propagation. Lead to lag, thumb is showing the direction of propagation. That means right hand circularly polarized. So we are coming from right hand circularly polarized to, we are coming from left hand circularly polarized to right hand circularly polarized when I only changed the direction of propagation, when I inverted the direction of propagation. Here what did I do? Inverted the phase but kept direction of propagation same. And all these are we are doing with respect to question 1. With respect to question 1 we are doing all these things. Now with respect to question 1, here what we are doing? With respect to question 1, here what is the direction of propagation? Minus Z. And here this is your lag and this is your lead. So with respect to question 1, we have inverted the direction of propagation as well. Along with that, we have inverted the phase difference as well with respect to question 1. Because in question 1, this was plus Z and this was lead. So both things we have inverted. So what will be the answer we are getting? Let's check that out. So who is at lead now? X is at lead. X is at lead. This guy is at lead. This guy is at lag. Where will be my Z? Z will be coming towards me, but the direction of propagation is in minus Z. That means direction of propagation is going inside the plane. You need to move your hand from lead to lag, moving my hand from lead to lag such that the thumb is pointing towards the direction of propagation. Lead to lag, thumb is pointing towards the direction of propagation. That means left hand circularly polarized. So what do you see here? If you made two changes, then from left hand circularly polarized to directly you are coming back to left hand circularly polarized. If you have made two changes, what all two changes? You have changed the direction of propagation as well, you have changed the phase difference as well. Then you are coming from left hand circularly polarized to again left hand circularly polarized. So what is the conclusion you can see from here? That let's just say I am having left hand circularly polarized here. What I am having? Left hand circularly polarized. So if I can do two things here. Invert phase only. Only means that I am not inverting the direction, and here invert direction of propagation only. So left hand circularly polarized will become right hand circularly polarized. Right hand circularly polarized. Now this guy will also have two options, right? This guy will also have two options. That you again invert the phase, invert phase only. Invert phase only. So if you again invert the phase, then what you will do? Left hand circularly polarized. Basically, we are going from left to right. Then same thing can happen with right to left as well, no? If you only invert the phase. Like just see this scenario. Here minus Z and lead. Here what is the scene? Minus Z and lag. So here what did you do? With respect to question 2, in question 4 what you are doing? With respect to question 1. Sorry, with respect to question 2, in question 4 what you are doing? Are you inverting the direction of propagation? No. You are only changing the phase. You are only inverting the phase. Here this was in lead. Here this guy is in lead. That's it. So here what you are getting? Right hand circularly polarized. Here what you are getting? Left hand circularly polarized. Say yes or no. In question 4, with respect to question 3, what you are doing? Are you changing the phase? No. This guy was in lead. This guy is in lead. But you are changing the direction of propagation from plus Z to minus Z. So what it has become? From right hand circularly polarized to left hand circularly polarized. Are you able to see why did I pick these examples? Because I am going to relate this thing with our next concept. Are you getting this point? So this is a very good concept. Like it will take very lesser time to answer the questions if you know this concept. Like if you have just find out for this one, then without even doing all these calculation, I can write down the circular polarization for all these guys. Just I need to see what is being changed. That's it, right? So that's why we did it. So invert only phase or invert the direction of propagation only. Invert direction of propagation only. So where you will where you will land at LHCP only. Same, this guy will also have two options. Or what you can say is that, if I invert both of the things, that invert phase and direction of propagation both. So where will I land? From LHCP to I will land at RSCP. Sorry. If I have inverted both, that means from LHCP to I will land at LHCP only. Because if both are inverted, so one inversion then another inversion, one inversion and then another inversion, you are landing at the same place, right? Or you can see from here, invert phase only and invert the direction of propagation, you are landing at LHCP only. The same thing is happening here. Okay, let's check more example. These are the conclusion that you need to keep in mind. Let's check more example. So what is the polarization here? If the phase shift is n pi, no matter even if the amplitude are different, if the phase shift is a multiple of pi, then certainly it is linearly polarized, right? No doubt about that. Here, if the phase shift is a multiple of pi by 2, then you can say it is circularly polarized, but the magnitudes are different. And if the magnitudes are different, then it is elliptically polarized. magnitude are same, but the phase shift is random. If the phase shift is random, you do not even need to look at these E naught. Random means whether either it should be a odd multiple of pi by 2 or it should be a multiple of pi. If both these two cases are not there, that means it is elliptically polarized. Right? Now what about this one? Phase difference, you see, very random. No need to see at the magnitude, nothing like that. Just if phase difference is random, that means it will be elliptically polarized. And here there is only one component of electric field. That means electric field is dancing only in one direction. There is no other component. If it is dancing only in one direction, let's just say if it is dancing in x direction only, then certainly it has to be linearly polarized only, because its component will be in x direction only. So certainly it has to be linearly polarized. If there is only one component, it has to be linearly polarized. So in the question someday, if I ask you that you need to get a linearly polarized wave from elliptically polarized wave, so what you will do? What I am asking, from elliptically polarized wave, you give me linearly polarized wave. So what you will do? You will say that, sir, please kill this y part. If you kill this y part, then I will be left with only x part. So it will be linearly polarized only. Or you can say, sir, please kill this x part. If you have killed this x part, then I will be only left with y part. So that will be linearly polarized. If I ask you from circularly polarized, I need linearly polarized. So you just kill one direction of propagation. If your electric field, I should not say direction of propagation, you should kill one of the component. If I say my electric field is dancing in x direction as well and y direction as well, and there is a very random phase shift between both of them, and what do I need? I need only linearly polarized wave. So what you will do? You will say that, sir, I will kill one of the component. If I kill one of the component, then forget about the phase shift. It will always be your linearly polarized wave. Okay, so that's it about the revisiting of polarization. After that, we are going to see our concept. Which concept? The concept of polarization at media interface. So this was just a revisit of the polarization that we have already studied. Also, we have seen some new conclusion here as well. Okay, thank you very much. Let's start it now, which I have already recorded. I will just add up the video now. Yeah, so let's start our chapter. So in this chapter, what we need to study? We need to study the polarization at media interface. What do I mean by that? Let's just say this is my boundary plane. So this wave is coming. Now this wave will be reflected back and some part will be transmitted. So now I am saying that my incident wave was linearly polarized. So what will be the nature of my reflected field? If my incident wave was linearly polarized, then what will be the nature of my reflected wave? That could be linearly polarized, or it is circularly polarized, or it is electrically polarized. And what will be the nature of my transmitted wave, whether it is linear, circular, or elliptical? That we need to find out. Okay. Now, when we studied normal incidence in our course, when we studied normal incidence, at that time we only consider one component of electric field. What I mean to say is that at that time, this is what we consider, that this is our propagating wave. This is our propagating wave, and electric field is dancing in x direction, and your magnetic field is dancing in y direction, and wave is propagating in z direction. So E cross H is your direction of wave propagation. This is what we considered. Now what I am saying is that now electric field is having two component. One component of electric field is dancing in x direction, and one component of electric field is dancing in y direction. Are you getting this point or not? Is this possible or not? Certainly it is possible, no? When we studied wave polarization, I told you, or even in the derivation of EM wave, I told you that wave can dance in two direction, in x as well, in y as well. It can never dance in z direction, but it can certainly dance in x direction as well. It can certainly dance in y direction as well. So it is having two components, EI1 and EI2. So basically your incident wave is combination of two component. One is dancing in x direction, another one is dancing in y direction, but there could be phase difference between them, right? It is not necessary that both are in the same phase. There could be phase difference between them. Basically, this is the scene. One is dancing in x, one is dancing in y. There is some phase difference. That's it. This is your incident wave. Certainly, this kind of incident wave you can get. So this is your incident field. Now, what will happen? There will be some reflections.
So this field will be, sorry, this wave will be reflected back. Now this wave will have two components as well. Now what will be the direction of those components, that I am not writing down. And this wave will be transmitted as well. So this is the transmitted wave. So this I am writing APR, sorry, and APT. Now let's take the cases one by one. In the first one, I will take a linearly polarized wave. What do I mean by that? The phase difference is the multiple of pi. So let the incident field be like this. This is my incident field, and I am taking the phase difference to be n pi. That means it is a multiple of pi. That means my incident electric field is linearly polarized. So this is the case I am taking. I will take all the polarization cases, linearly, circular as well. So these cases I will take. So my incident electric field is linearly polarized. This is what I am saying. So how I can write down my field? Can I write down my field in this manner? E naught 1, and one component is dancing in x direction, e to the power my wave is going into z direction, plus there is a phase difference. The other component, there are two components of electric field, one is dancing in x, one is dancing in y. So other component is dancing in y direction, having an amplitude of e naught 2, and wave is certainly traveling in z direction only. Can I write down my field in this manner? Here, how will the field look like? This phase component, this phase I am taking as 0, because I want this field to be linearly polarized. So if I take the phase to be 0, that means it is linearly polarized, right? So what kind of field I will get? E to the power minus j beta z ax cap plus, here let's write beta 1 because this is the incident medium. So beta 1 I am writing, medium 1. Beta 1 shows medium 1. This is your medium 1, no? E naught 2 e to the power minus j beta 1 real. Now, if your reflection coefficient is positive, what do you mean by reflection coefficient to be positive? That means neta 2 is greater than neta 1. What about our reflection coefficient? Our reflection coefficient either could be positive or it could be negative, right? And why I am interested in reflection coefficient? Because I need to find my reflected wave. I need to find my transmitted wave. These two waves I need to find. So if I know my reflection coefficient, what I am assuming, let my reflection coefficient is 0.5. So what will be my transmission coefficient? That would be 1 plus gamma, that would be 1.5. So if this is positive, certainly always transmission coefficient is positive only. Always transmission coefficient is positive only. So now I am saying that if my reflection coefficient is positive, then let me know how will this diagram look like. This diagram will look something like this. That if it is positive, then electric field will never change its direction. Now let me know one thing. When we were studying our normal incidence, at that time what did I say? That I have only one electric field component. So for that I used to find my reflection coefficient, and then I used to multiply. I used to find my reflection coefficient, and then I used to multiply this reflection coefficient with the magnitude of incident wave, with the magnitude of incident electric field, and by multiplying the magnitude of reflection coefficient with EOI, I used to get my reflected electric field. Say yes or no. Now this electric field is having two components. One is like this, another one is like this. One is like this, another one is like this. So both will be multiplied with the same reflection coefficient. No. Like in oblique incidence, we have reflection coefficient for parallel polarization, for perpendicular polarization, and both are not equal. Both have different formula. But in oblique incidence, whether you take this field or you take the field in this direction, for both of them, the same reflection coefficient will be there. No. Like if I call the reflection coefficient for this one as gamma E1, and if I call the reflection coefficient for this one as gamma E2, so can I say that my gamma E1 will be equals to gamma E2 will be equals to gamma E? Because both of the electric fields are parallel to the boundary plane. This is my boundary plane. One electric field is dancing like this. One electric field is dancing like this, which is parallel to the boundary plane. And one electric field is dancing like this, in this direction, which is parallel to the boundary plane. So for both of the electric fields, the reflection coefficient value is same. This is what I want to tell. So that means if my E naught 1, what I mean to say is that if my E naught 1 is being multiplied with 0.5, that means my E naught 2 will also be multiplied with 0.5 only. So can I write down my reflected electric field? So that would be multiplied by 0.5. Will there be any phase change? We are considering both of the medium to be lossless. Okay, we are considering both of the medium to be lossless. If both mediums are lossless, then what is the reflection coefficient? Neta 2 minus neta 1 divided by neta 2 plus neta 1. Real, 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 real. If both are lossless, all are real, that means this complete gamma E is real. And if it is real, that means it will not have any phase. And if it is not having any phase, so directly 0.5 will be multiplied. Let's just say it was having some phase, e to the power j, some alpha, some phase alpha it was having, and let's not take alpha. Let's just say it was having some phase phi. So now the phase phi would have been multiplied here. Are you getting this point? Right? But as of now, there is no phase. So e to the power minus j beta z beta 1 z ax cap plus 0.5 e naught 2 e to the power minus j beta 1 z ay cap. What kind of polarization is that? In the reflected field, you only change the magnitude, and both of the magnitude was changed with the same amount, and there is no change in the phase. Previously phase difference was 0. Now as well the phase difference is 0. What I mean to say is that still the phase difference is equal to 0. That means still it is linearly polarized. Say yes or no. So I will tell you a statement. You let me know whether it is correct or not. So an incident wave, let me repeat it. A linearly polarized incident wave will give linearly polarized reflected wave in case of normal incidence. Is that statement correct? Yes. If a wave which is linearly polarized is incident on a dielectric medium, then your reflected wave will be linearly polarized only. Is that statement correct? Yes. Now here both of the mediums were lossless. Now even if the medium was lossy, still the statement would be correct. Why is that so? Because even if the mediums were lossy, still the statement would be correct. Why is that so? Can you think about it? If the medium was lossy, then what would have been your reflection coefficient? It would be somewhat like this: 0.5 e to the power j some phase. Let's just say the phase is 30 degree. It could be anything. I am assuming the phase is 30 degree. Now this reflection coefficient will be multiplied with this guy as well, and it will be multiplied with this guy as well. Basically here you will have 0.5 e to the power j 30 e naught 1 e to the power minus j beta 1 z ax cap plus 0.5 e to the power j 30 e naught 2 e to the power minus j beta 1 z ay cap. What is the phase difference now? Still it is 0 degree. Here it was 0 degree. Still the phase difference is 0 degree only, because this is also leading by 30 degree. This is also leading by 30 degree. Then again the phase difference is 0 degree. So again it is linearly polarized. So whether the mediums are lossless or lossy, if your incident wave is linearly polarized, then certainly your reflected wave will be linearly polarized only in case of normal incidence. The incidence is normal. We will study the same kind of scenario for oblique incidence as well. But as of now, we are talking about normal incidence. Is that concept clear? Is this thing clear to you or not? But we are going to consider only lossless medium. So in your notes, you can write down that this is applicable for lossy medium as well. Somewhere you can write down. But this is only the reflected wave we have seen. What about transmitted wave? So what will be your transmitted wave? 1 multiplied 1.5 with E naught 1. What is the direction of wave propagation? That is plus Z only. But here beta 2 I will write, because the wave is going into medium 2. So beta 2 AZ minus J beta 2 Z cap. Electric field is dancing in the same direction. And here also E naught 2 e to the power minus j beta 2z, because we are talking about medium 2, and electric field is again dancing in y direction. So again the same case, linearly polarized. So both incident and reflected wave, both reflected and transmitted wave, both are linearly polarized. Transmitted and reflected wave both are linearly polarized. Say yes or no. Now let's take the case of gamma is negative, and that will happen when neta 1 is less than neta 2. Okay, and what I can let my reflection coefficient is, let's take the phase as well now. Okay, if we don't consider both of them to be lossless, then it will have some phase as well. So can we take the phase? But Here we did not take the phase, so student will be getting confused. So in your notes somewhere you can write down this thing. Like you wouldn't be having much space. You can try writing down here that the same analysis will remain for lossy medium as well, but there is high chances that they will ask for lossless medium only. So let's assume lossless medium only. Okay. Let reflection coefficient to be minus 0.5. But transmission coefficient will always be positive only because it is 1 plus 1 plus reflection coefficient, that is 0.5 only. Okay. So let's write down the reflected electric field. So what that would be? If reflection coefficient is negative, that means electric field is changing its direction. What does that mean? That electric field which was dancing in x direction, that will dance in minus x, and electric field component which was dancing in y direction, that will dance in minus y. How will the reflected electric field look like? This was the incident one. So this was dancing in plus x, now it will dance in minus x. This was dancing in plus y, now it will dance in minus y. This is the case for reflection coefficient being negative. If reflection coefficient is negative, then this is the case. If reflection coefficient was positive, then what would be the case? If reflection coefficient was positive, then this would have been the case. But now since it is negative, then the positive one is dancing like this and the negative one will be dancing like this. I hope you remember all the assumptions that we made when we were doing the derivation, because I showed you the derivation only because the assumptions were very necessary. Although in this topic, in normal incidence is very straightforward. Here assumption doesn't take that much role. But when we talk about oblique incidence, their assumption is very important. So again we will discuss that thing. So I hope you remember all those things. Otherwise you will not be able to solve these kind of questions perfectly. So now we are assuming it to be minus 0.5. So what is happening here? Basically the direction of dance will change. This was dancing in x, this was dancing in y. Now this is dancing in minus x. Minus sign I have already put here. Or let's put the minus sign here as well. And now the other one is dancing in, although it was E01, this is E02. Now other one is dancing in AY. But will it change anything? What I mean to ask is that, will it change the linear polarization to anything else? No. Still the phase difference is 0. Here since it is dancing in minus y, that means it has a phase of pi. Can I write down it as a phase of pi? If I need to write down plus ay, so can I write it down in this manner? Say yes or no. And if I need to write down plus ax here, plus ax here, then I can also give it a phase shift of pi. This can also get a phase shift of pi. So what is the phase difference? Again it is 0. Phase difference is still 0. And if phase difference is 0, then certainly it is linearly polarized. And what about the transmitted wave? You can directly see what about the transmitted wave. Transmitted wave will also be, here beta 1 was there, but here it would be beta 2. Transmitted wave will also be linearly polarized only. This was very easy case actually. This was a very easy case. So let's write down the note. We will not write down summary. I am only telling the statement. What is the statement? In case of linear polarization, when a linearly polarized EM wave when a linearly polarized EM wave is incident normally on a dielectric boundary surface, then it will reflect back and will give you linearly polarized wave only, and on transmission as well it will give you linearly polarized wave only, no matter whether your reflection coefficient is positive or negative. Is that statement clear? So this is the first statement we are getting from here. These kind of statements we will get, and statement wise question can be asked. Although theoretical or numerical question can also be asked, but statement wise question can be asked for sure here, right? So this was the first case. Now my wave is circularly polarized because your phase shift is odd multiple of pi by 2. So my wave is circularly polarized now. That means also the condition should be that E01 and E02 should be equal. Phase difference is 2n plus 1 pi by 2, right? What is my incident field? E naught. Here E naught 1 and E naught 2 are equal. So E naught 1 and E naught 2 are equal to E naught. So that would be, this is dancing in x direction having 0 phase, dancing in x direction having 0 phase, and the wave is propagating in z direction. What about the other one? It is dancing in y direction having the phase difference of pi by 2. Can I write it down in this manner? I am taking phi to be, let phi to be pi by 2. This is what I am assuming, because this is also circularly polarized, and this is dancing in, this is also propagating in z direction only. And what do I see here? What is this? This is your left hand circularly polarized. You can see this case, first case we took E naught e to the power minus j beta z ax cap, E naught e to the power pi by 2 e to the power minus j beta z ay cap. This is the same case, or you can check out from here as well. Very simple. This is left hand circularly polarized wave. Now again we need to take gamma e is equal to positive. If gamma e is positive, what does that mean? I can take gamma e to be 0.5 I am taking, and what will be the transmission coefficient? That would be 1.5. So if I write down the reflected field, so both the component will be multiplied with 0.5. Both the component will be multiplied with 0.5. Okay, there is a very big blunder I did here. This was this one. The wave will propagate in negative z, na? The reflected field will propagate in negative z. The reflected field will propagate in negative z. So that was a very big blunder from my side. The transmitted wave will propagate in plus z only, but the reflected wave will propagate in negative z. So I am writing the reflected wave. So what will be the reflected wave? See it very carefully. That would be E naught e to the power plus j beta z, beta 1 z, write down, plus j beta 1 z ax cap, plus 0.5 E naught e to the power j pi by 2 e to the power plus j beta z ay cap. What do you think? What kind of polarization is that? Circularly polarization, because same. What is the phase difference? Pi by 2, circularly polarized. Whether it is left hand circularly polarized or right hand circularly polarized. If you compare both of the expressions, phase difference same. Y is leading, Y is leading. This wave is propagating in plus Z and this wave is propagating in minus Z. Phase difference is same, only the direction of propagation is changed. That means left hand circularly polarized will become right hand circularly polarized. An awesome point and can be asked in your examination. Are you getting this point or not? Here phase did not get changed because gamma E is positive. Phase did not change. Right? Gamma E is real, so phase did not get changed. But only the direction of propagation got changed, and because of that, left hand circularly polarized became right hand circularly polarized. And what about the transmitted one? What about the transmitted one? 0.5 E naught, not 0.5, 1.5. 1.5 E naught. Now this will be propagating in plus Z only. Ax cap plus 1.5 E naught. Phase is pi by 2 only, and this will be propagating in plus Z only. So this is your left hand circularly polarized only, because here polarization did not get changed. The phase difference is also pi by 2 and the direction of propagation is also same. These are completely same, just the difference is the beta. Beta is changed, although all these are same only. So beta, this guy doesn't matter in wave polarization. This guy doesn't matter in wave polarization. Only who matters? Only two things matter. Only two things matter. What all are those things? That what is the phase difference and what is the direction of propagation. इन सब का मीम मत बनाना यार तुम लोग, मैं ये बोलते हुए अटकता हूँ जो, ठीक है, मीम वगैरह मत बनाना. Yeah, so only two things matter, that is the direction of wave propagation and the phase difference. Okay, also amplitude also matters, this also matters, amplitude also matters. So amplitude is here is also same. So this is left hand circularly polarized. Is that clear to you? If you are taking full concentration, then all these things would be clear to you. Now even if the mediums were lossy, still the answer would remain same. Why is that so? if the mediums were lossy, then what would have happened? This would have some phase. This reflection coefficient would have some phase. So this was having some phase. But now this phase will be multiplied to this guy as well. It will be multiplied to this guy as well. It will be multiplied to this guy as well. It will be multiplied to this guy as well. So it will not change the amplitude. Now, will it change the phase? It will change the phase, but for both of the cases. It will change the phase for x as well. It will change the phase for y as well. But the phase difference will remain same. So even if the medium is lossy, still all the analysis remain correct. Say yes or no? So you can just write down the summary here as well. Here I will write down the summary. All the analysis, all these analysis remains correct for lossy medium as well. Right? And in the examination, like either they will give you this data or you can take any random data based on your understanding. Right? Now if gamma E is negative, so if gamma E is minus 0.5 I am taking, so my tau E would be 0.5. So what will be my reflected field? This you should do on your own and let me know what will change, left and right, and just let me know what will change now. So here, since minus sign is there, that means the reflected wave, the reflected electric field will change its direction. So can I compensate this minus sign? Yeah. How I can compensate this minus sign? Using e to the power j pi. Say yes or no. Then Ax cap. And 0.5 E naught e to the power j beta 1 z. Here as well there will be minus sign. Here as well there will be minus sign. But that I am compensating. How I am compensating? Using e to the power j pi. It is already having a phase of e to the power j pi by 2 that I cannot change. Say yes or no. This will be the expression, right? Already the phase difference was pi by 2 that I am putting. Now this is your more phase that is coming because of the reflection coefficient. That means they are changing their direction. Now this is dancing in x, this is dancing in minus x, and this is also dancing in minus y as well. Minus y and minus x. But now you let me know one thing. What all changed here? The direction of propagation got changed. Did the phase difference change? No. Phase difference is still the same. Here y is leading, here also. In this case y is leading, here also y is leading. Just the direction of propagation got interchanged. That means this left hand circularly polarized became right hand circularly polarized. E transmitted. What that would be? 0.5 E naught e to the power minus j beta 2 z Ax cap. Nothing will happen, nothing changes will happen to this phase, that is there as it is. E to the power minus j beta 2 z Ay cap. What do you think? What kind of polarization it would be? Compare this and this. Y is leading, Y is leading. Wave is propagating in plus Z, wave is propagating in plus Z. What kind of polarization? Sorry, left hand circularly polarized. Are you getting this point? And and one more thing to notice here is that these components are not changing. If these would have changed, then instead of circularly polarized, here I would have been writing elliptically polarized, right? These are remaining the same. So what is the conclusion here is that, what is the conclusion? The conclusion is, in case of normal incidence, if the incident electric field is left hand circularly polarized, then reflected electric field will be right hand circularly polarized, no matter whether your reflection coefficient is positive or negative. And certainly your transmitted electric field will be left hand circularly polarized only, whether your transmission coefficient, whether your reflection coefficient is positive or negative. So there is no role of reflection coefficient being positive or negative. Just the conclusion is, in the case of normal incidence, if your wave is linearly polarized, then reflected wave will also be linearly polarized and transmitted wave will also be linearly polarized. But if your incident wave is circularly polarized, then also reflected and transmitted wave will be circularly polarized, but the direction will change. How the direction will be changing? How the direction will be changing? the direction will be changing in a manner that left hand circularly polarized will become right hand circularly polarized at the reflection, but at the transmission left hand circularly polarized will be left hand circularly polarized only. Is that clear to you or not? Let's answer this question. Just answer this question. A left hand circularly polarized EM wave propagating in a lossless dielectric with in a lossy dielectric. Here I will write lossy dielectric now. Okay. In a lossy dielectric, because for lossy dielectric as well the same analysis is there, and same analysis will be there for electrically polarized as well, right? Because in electrically polarized what happens, there is a random phase. Now reflection coefficient is being added in both of the component, in parallel component as well and in perpendicular component as well. Sorry, in this component as well, in this component as well, and in this component as well. In both of the component the same reflection coefficient is being multiplied. So if same reflection coefficient is being multiplied, that means magnitude is also changing by same and phase is also changing by same. The only thing is here the direction was changing. So here only the new thing came up. What is the new thing that came up? So only you need to remember this thing, that if incident wave is right hand circularly polarized, then reflected wave will be left hand circularly polarized. Rest all will remain as it is in case of normal incidence, right? So in case of normal incidence, if you want to remember only one conclusion, then that is the conclusion is like, if they want to ask any question, then I guess they will frame question on this one as well. Only this one they will frame the question. What they will say is that for normal incidence, we are studying normal incidence only. So left hand circularly polarized EM wave at normal incidence will reflect back as right hand circularly polarized, and vice versa, okay. I don't know the spelling of vice versa, and opposite is also true. This is what I used to write down in the English examination. Opposite is also true. Okay, so opposite is also true. Left hand to right hand to left hand. Rest all things will remain as it is. So can you answer this question? So here these epsilon value are given just to confuse you. You just know that left hand circularly polarized will give you right hand circularly polarized. Now let's make it right hand here. Otherwise people will think that this is only applicable from left to right, but no, opposite is also true, no? So let's make it right. So RHCP will transmit as RHCP only, and here RHCP will be reflected back as LHCP. RHCP will be reflected back as LHCP, and here RHCP will be reflected back as LHCP. So which statements are correct? 1, 2 and 3. These statements are correct, because at the transmission you will always get RHCP, and at the reflection the circular polarization will change, right hand to left hand and right hand to left hand, no matter whatever the value of gamma is there. Okay. Now we need to see the same case in oblique incidence. Now that is more interesting, way more interesting than normal incidence. Okay, here you need to think about magnitude as well. Here you need to think about everything. Okay, so that we will start, but I need to take a break because of my throat again. So then I will come back and we will start studying about oblique incidence. Yeah, so let's start the oblique incidence case. And keep your full concentration here, then only you will be able to understand. Okay, just keep full concentration here. And solve it with me as well, like in your rough notebook as well, you should be doing the things. So when we studied oblique incidence, we studied two kind of cases there, perpendicular polarization and parallel polarization. And there we introduced one term. What was that? Plane of incidence. Do you remember what was plane of incidence? Plane of incidence. Do you remember what was plane of incidence? So this was our boundary plane. This is how the incident wave was coming. This is how the wave was being reflected, and this was the transmitted wave. So all these incident, reflected and transmitted wave will be in one plane only, and that plane was known as plane of incidence. So here, looking at this geometry, can you tell me what is my plane of incidence here? Here my plane of incidence is XZ plane. Why is that so? Because my wave is striking xy plane. This, what is this? This is my xy plane. If I call this as x, this as z, so where will be my y? Y will be coming towards me. So my wave is striking on this plane, that is xy plane. So this is incident, reflected, and transmitted. All are in one plane. What will be that plane? That will be coming perpendicular to it. That will be coming perpendicular to it. So this will be the plane of incidence, and the plane of incidence will be xz plane. So that is of no use, but I will again and again use this term, plane of incidence. Now we studied parallel polarization. When we studied parallel polarization, what did I say? That your electric field is parallel to the plane of incidence. So this is how my incident electric field was there. This was my incident electric field, because this is my incident wave. This is my incident wave. So how will be my incident electric field? Incident electric field can be there in this direction as well, in this direction as well. But we generally used to assume this direction. So I am assuming that this is my incident electric field. This is my incident electric field. Okay. So I am only talking about parallel polarization. So in case of parallel polarization, we studied this incident electric field. So where was our magnetic field? Our magnetic field was coming towards me, because E cross H should give me P. So this is my direction of wave propagation of incident wave, and this I used to consider as my HI. I am just telling you the scenario of oblique incidence, just revisiting the scenario of oblique incidence. Now we derived for parallel polarization, we derived the value of reflection coefficient. For parallel polarization, we derived the value of reflection coefficient. What was that? Neta 2 cos theta t minus neta 1 cos theta I divided by neta 2 cos theta t plus neta 1 cos theta I. Now this reflection coefficient was only true for an assumption. Are you getting this point or not? Do you remember this point or not? This was true only for assumption. What was the assumption? The assumption was the incident and reflected magnetic field will be in the opposite direction. Whenever we have studied our oblique incidence or normal incidence, whether it is parallel polarization or perpendicular polarization, we have always made an assumption. What was the assumption? That electric field never changes its direction. But in case of parallel polarization, electric field has to change the direction, because if this is my reflected wave, if this is my reflected wave, then my electric field could be either in this direction or in this direction, which is not same as the incident wave. So here certainly my reflected electric field will change the direction. It is not opposite, but certainly it is changed. Either it could be here or it could be here. So the assumption we cannot make with respect to the incident electric field. That's why we made the assumption with respect to the incident magnetic field. And what did I say is that the incident magnetic field will change its direction. This was the assumption that we made, that this is our HR. Do you remember it? And now with respect to this HR, what will be my ER? So with respect to this HR, my ER will be like this, because E cross H should give me P. So with respect to this HR, this will be my ER. Are you able to relate these things or not? So this was the assumption that we made. And certainly, if this is the incident electric field, then this will be the transmitted electric field. Here, if I ask you, the transmitted electric field and incident electric field, both are in the same direction? Again, no. Although their orientation is same, but the direction is not same, because here the angle is theta t, here the angle is theta I. So you cannot say the direction is same, although orientation is same. And here your incident magnetic field is going towards me. So here as well the transmitted magnetic field will be coming towards me. Okay, here I said, I guess I called it reflected electric field as of now, as far as I, like just now I called it reflected electric field, but this is transmitted electric field. Okay. So if I ask you, if my incident electric field and transmitted electric field both are in the same direction, then you will say no, both are not in the same direction. They are, this is having an angle of theta I and this is having an angle of theta t, but the orientation is same. The orientation is like this only. Is that clear to you? So this is how we studied parallel polarization. Now come to the perpendicular polarization. Perpendicular polarization. So in perpendicular polarization, what was the formula? Neta 2 cos theta I minus neta 1 cos theta t. The trick also I told you is perpendicular. That means they are perpendicular to each other. So neta of this one, theta of this one. Neta 2 cos theta I plus neta 1 cos theta t. Right. So let's make the diagram for Now we are making the diagram for perpendicular polarization. So there in the perpendicular polarization, either I can assume my electric field to be here, or I can assume my electric field to be going downward. I can assume anything. As of now, I am assuming this is my electric field. This is my incident electric field. Now with respect to this incident electric field, where will be my magnetic field? My magnetic field could be either here or here. But with respect to this incident electric field, where will be my magnetic field? You need to see it. E cross H I need to do. So that magnetic field has to be downward. Because what I need to do? E cross H. If you see E cross H. E cross H. Yeah. E cross H. So magnetic field has to be here. Here has to be my magnetic field. See H cross E. Yeah. Using the right hand, H cross E is giving me this one. Sorry. It would be opposite. Really sorry. This would be opposite. Here would be your incident electric field. Incident magnetic field. Sorry. Because E cross H I need to do. Where is my E? My E is coming towards me. So E cross H. This is my direction of propagation. E is coming towards me cross H. And what was the assumption that I made? That electric field never changes its direction. So here electric field will not change its direction because it is perpendicular to the plane of incidence. So this is your incident electric field and this will be your reflected electric field and this will be your transmitted electric field. So this was the assumption that were made. So always I told you there was one question as well. If you don't remember the assumptions, then that question will be wrong. And that question was wrong by IITs as well. And in a lot of coaching institute material as well, that answer is still given wrong. Okay. So there also I proved it. So assumption was very, very important. Right. So this was the assumption. Now with respect to them, you can make the magnetic field as well. Because if you know the direction of E, if you know the direction of propagation, then you can write down the magnetic field as well. But that is not our matter of concern. So when we were studying parallel polarization, at that time we only considered the parallel case from the plane of incidence. And when we were studying perpendicular polarization, at that time we only consider the perpendicular case. But what if both are together present? Did we solve one question on that? Yes. Where perpendicular polarization was also there and parallel polarization was also there. That means what I mean to say is that my incident electric field is a combination of parallel polarized wave and perpendicular polarized wave. That means what I mean to say is that this is how my incident electric field is there now. My incident electric field is having two components. It is having a parallel polarized wave as well, and it is having a perpendicularly polarized wave as well. Since it is incident, that's why I am putting EI. And both can be phase shifted by some number as well. So both can have some phase shift as well. Are you getting this point or not? Parallel polarization, perpendicular polarization is also there. That means one component will be like this and another component will be coming towards me. It could be going into the plane as well. There is no hurry in that. There is no doubt in that. It could be going into the plane as well. I am just assuming that one component is coming towards me. This is not the magnetic field I am drawing. I am drawing the electric field, right? This is the electric field that I am drawing. This is the perpendicular component for incident wave. So this is the electric field I have drawn. Similarly, when we studied the normal incidence case, here also I told you, no, there could be two components. So here also there are two components. One component is dancing in xz direction, this component is dancing in xz direction, and this component is dancing in y direction. This is the case of perpendicular polarization, perpendicular, and this is the case of parallel polarization. So now my E field is combination of two fields, perpendicular polarized wave and parallel polarized wave. Both of the electric fields are there. So certainly in the reflected field as well, there will be both of the cases. But how will I make my reflected field now? I will make my reflected field in this manner. In which manner? When I only consider parallel polarized wave. When I consider only parallel polarized wave, so what will be my reflected electric field? This is how my reflected electric field will look like. If you remember it, just before some seconds, we draw this diagram. When we were studying about this one, we drew this diagram. What was the assumption we made? That magnetic field is changing its direction. So for this case, magnetic field was coming towards me. For the next case, magnetic field was going into the plane. That means this will be my reflected electric field. So this is the parallel component of reflected electric field. And for perpendicular polarization, what is the assumption we make? That electric field never changes its direction. So this is how I will make my, sorry, for perpendicular polarization, this is what we make. For perpendicular polarization, what is the assumption we make? That electric field never changes its direction. So if incident electric field is coming towards me, then your reflected electric field will also be coming towards me. And same goes here. This orientation will be same as it is. Although the direction is not completely same, but the orientation is same. So this is going towards here. This is also be going towards here. This is coming towards me. So this will also come towards me. This is the parallel component of that transmitted wave. And this is the perpendicular component of the transmitted wave. So are you understanding what we are doing here? We are breaking two parts of electric field. One is parallelly polarized, one is perpendicularly polarized, and both are having some phase difference. Now if the phase difference is 0, then it will be linearly polarized. If the phase difference is pi by 2, then it will be circularly polarized, and if the phase difference is something else, then it will be elliptically polarized. And with respect to that, we need to study this chapter now. That if my incident electric field is linearly polarized, that means what kind of reflected field I will get. Are you getting this point or not? So that's why we introduced this thing. We solved a question as well. If you remember the IIT, I don't remember from where it was. It was an MTA. So there you were having two component of electric field. And then I told you that everyone is solving this particular question by boundary condition. But without even applying the boundary condition, with applying these formula as well, that question can be solved. And there I told you that I broke the question into two parts. One with the parallel polarization, one with the perpendicular polarization. And then we applied the formula for both of the cases. And with the assumption in our mind. Assumption should always be in our mind. In case of parallel polarization, what was the assumption? In case of parallel polarization, the assumption was that magnetic field changes their direction. But in case of perpendicular polarization, what was the assumption? The assumption was electric field will never change their direction. And if we keep the assumption in our mind, then we can apply these formula. So these formula are derived with respect to this assumption that in case of perpendicular polarization, all my electric field are coming towards me. 1, 2, 3. All electric field are in the same direction. It is not necessary that it should be coming towards me. It could be going into the plane as well. But all are in the same direction. And in case of parallel polarization, the assumption is here with respect to this, whatever the magnetic field I get, and with respect to this, whatever the magnetic field I get, will be in the opposite direction. Do you remember these things or not? This is just a revision of everything that we have studied. So now I am saying that my incident electric field is having two components. One is parallelly polarized and one is perpendicularly polarized. And both are having a phase difference of pi. Now with respect to that pi, I will get linearly polarized and circularly polarized wave. And with respect to that, what will be my transmitted wave and what will be my reflected wave, that we need to study. And here, this is my reflection, this is my reflection coefficient, and this is my reflection coefficient for which case? For parallel polarization case, and this is my transmission coefficient. So this is my reflection coefficient for perpendicular polarized case. And one thing I am pretty sure that these two can never be equal because formulas are different. Formulas are different, no? So these two can never be equal. So here your wave is having two components. If I find the reflected wave, then parallel component will be multiplied with gamma parallel, and your perpendicular component will be multiplied with gamma perpendicular. And if both are being multiplied with different thing, that means their amplitude will change now. That means E01 and E02 will change now. In the previous case, what was happening? In case of normal incidence, both were being multiplied with the same number 0.5, 0.5, 0.5. Because for both of the fields here, the reflection coefficient was same. But here there are two kind of electric field. One is dancing parallelly, one is dancing perpendicularly. For this one there is different reflection, and that will change the reflected electric field, and that will change the orientation, that will change everything. So that's why this topic becomes very important. I hope you are understanding what we are doing here. Say yes or no. Right? I'm having elaichi again in my mouth. So again and again I say this thing. I'm not a fan of Ajay Devgan. I'm not having anything else. Only elaichi I am having. So don't think that I am chewing pan masala. No. Okay? Because elaichi is good for the throat. If you are having the throat pain, then you can have elaichi and it can be gone. So that's why I am having it. So let's get back to our concept now. So what I am saying, phi is equals to n pi. So incident wave is linearly polarized, that I know. So now we need to consider two kind of reflection. One is the ordinary reflection. The other one is total internal reflection. So these two kind of reflection we need to understand. So now in the ordinary reflection, like that means there is no total internal reflection. So in case of that, what will be my reflection coefficient? This reflection coefficient. Certainly it will be a real quantity, na? Because I am considering both of the medium to be lossless. In this case, we will always consider the medium to be lossless only. Forget about lossy medium, okay? Or we can take the lossy cases as well. So here, gamma parallel is real and gamma perpendicular is also real. But one thing I am pretty sure that these two are never equal. These two are never equal. So if I write down my reflected electric field, what I am writing? Reflected electric field. So this is having two components. One is the parallel component and one is the perpendicular component. Now how this will be coming into action? How this component will be coming into action? Now I am not writing down the direction. I am only writing down the magnitude. Okay. So how this will be coming into action? It will be multiplied with gamma parallel with E parallel of incident wave. Say yes or no. How will you write down this component? You will, when you write down this component, it will be multiplied with gamma parallel with incident electric field parallel component only. Say yes or no. Are you able to understand this point? Parallel component of reflected wave will be equals to the parallel reflection coefficient into the parallel component of incident wave. Say yes or no. Right? Here I am not putting the direction. Why I am not putting the direction? Because incident and reflected electric field are not in the same direction. This is the direction of incident one. This is the direction of reflected one. So they are not in the same direction. So that's why I am not putting the sign. Because sign doesn't matter. The direction of E field doesn't matter here. Here what we need to see? We need to see the phase. We need to see the phase. We need to see our magnitude of both of the waves, and along with that, what we need to see? We need to see what is the direction of propagation. Those things we need to see, right? So this is your, this case is there. Then plus what about the perpendicular polarization? So now perpendicularly wave will be this one. Say yes or no, right? Now this is a real quantity, but these two are different. This guy and this guy is different, but they are not making any phase difference. What I mean to say is that they are not, if my incident, let's write down my parallel field component. I am writing down my parallel field component. So it is having some magnitude E01 e to the power where my wave is propagating. My wave is propagating in plus z and plus x. So something would be coming here that I don't want to write, and something would be coming here. So my wave is propagating in plus x and plus z, and where is my electric field? That direction will also come. So now the thing is, this E01, the magnitude will be multiplied with gamma parallel, and that is a real quantity for a lossless medium. Considering lossless medium, for a lossless medium, it is a real quantity. Say yes or no. But it is not having any phase. That means here phase is 0. Gamma doesn't have any phase. Phase is 0. So if phase is not getting changed, that means the parallel component and perpendicular component have changed their magnitudes. Here your gamma parallel will be multiplied with E01 and something would be coming, and here this perpendicular component will be multiplied with, let's just say this perpendicular component, incident perpendicular component was having a magnitude of E02. This is what I am assuming. And e to the power minus j beta 1, something was there, e to the power minus j beta 1. This something z and x component was also there, and they were dancing in some other direction. That I don't know. Just the thing is, this E02 is multiplied with gamma perpendicular, right? This E02 is multiplied with gamma perpendicular. So the thing is, phase difference did not get changed. Here, phase difference remains the same. Phase difference remains the same. So if phase difference remains the same, that means phase difference is equals to n pi only. And what does that mean? It is linearly polarized only. So in the examination, what you will be thinking? Okay, sir, both of the mediums are lossless. Both of the mediums are lossless. That means reflection coefficient for perpendicular polarization and reflection coefficient for parallel polarization. Both will be real quantity. Both will change the magnitude, but they will never change the phase. And if they are not changing the phase, then I don't have any issue. The linear polarization will be linear polarization only. Only the magnitude will be changed. That means if the linear polarization was like this, let's just say previously linear polarization was like this. In this manner, linear polarization was there. Then now this slope of the line can change. The line can come here either the line can come here or the line can go like this. So the slope of line can change, but it will be linearly polarized only. Is that clear to you? Are you able to visualize? If there is no phase change, then it is all fine. But now if the medium were lossy, let me add a page for lossy medium. What I am writing, just 1 second. For lossy medium, what will be the case? For lossy medium, the case will be that gamma perpendicular will be there. It will have some phase, sorry, it will have some magnitude, and it will have some phase as well, no? Because what is the formula of gamma parallel? That is neta 2 cos theta t anything. And if your medium is lossy, then neta 2 will be complex. And if it is complex, then complete your expression will be complex only. So this will be complex. And what about your gamma perpendicular? So it will also have some magnitude, and it will also have some different phase. So here magnitude are also not same, and phases are also not same. So what will happen now? If I write down my reflected electric field. So if I write down my reflected electric field, so this is your reflection coefficient. It will be multiplied with E01. This will be multiplied with E01, and something would come here, plus this is your reflection coefficient, and it will be multiplied with E02, and something would come here. What was this component? This was the perpendicular component, and this was the parallel component. Now, previously the phase difference was 0. Here I consider phase difference to be 0. Let phi equals to 0. Here phase difference was 0. What I am considering here is that, here what I have considered, here phi equals to 0. This phi equals to 0 I have taken. This phi equals to 0 I have taken. That's why I can write it down. So here I have considered phi equals to 0. But now what is the new phase difference? New phase difference. So now the new phase difference is phi 2 minus phi 1, which is not, it is not necessary that it will be a multiple of n pi. That means here whatever the magnitude is there, that I don't care, but now the phase difference has changed, and if the phase difference has changed, that means elliptically polarized. So this is how you need to think in the examination. What you will be thinking? Okay, sir, this is the case of let me pause the video. Yeah. So in the examination, how will you think? So in the examination, first it will be given that both are lossless medium. If both are lossless medium, then there is no doubt that reflection coefficient and transmission coefficient both will be different, but both will not add up any phase. If they are not adding up any phase, then linear polarization will remain linear only. But if both of the mediums are lossless, so if both of the mediums are lossy, then what will happen? The reflection coefficient will add up some phase, and if it is adding up some phase, what does that mean? That means they are disturbing the phase difference. Previously the phase difference was 0, but now they have disturbed the phase difference, and if it is not the multiple of pi, it has been disturbed, then your wave will be elliptically polarized. Is that clear to you or not? What about the transmitted wave? What about the transmitted wave in this case? Now here you would be saying that, sir, you are not considering the positive negative thing. Like what if gamma parallel was positive, what if gamma perpendicular was negative? So that I am putting on you. And also we will solve one question where we will take gamma parallel to be positive, gamma perpendicular to be negative, gamma parallel to be negative, gamma perpendicular to be positive. So that question also we will take. But as of now in the theory, we cannot cover this much things, right? Like I am taking all possible combination. In the examination, one combination will be asked. So there you need to think. So here I am not giving any conclusion or anything like that. Just you need to think in this manner. That's why we are teaching it. So you are developing your problem solving skills here, that in the examination, if these kind of questions are coming, then how you will think there. So this is how you will be thinking. Now what about that transmitted field. Reflected field, reflected wave we have talked about. Let's talk about the transmitted one. So for lossless medium, we need to talk about transmitted one. For lossless medium. So what will be your transmission coefficient? Certainly these two will not be equal. Certainly these two will not be equal. Say yes or no. But they will be real. Both will be real. So here you can see that both are real. That means not having any phase. Real means not having any phase. And from here, what did you get to know? That a phase difference is not disturbed. And if phase difference is not disturbed, then what is the answer? Linear polarization only. Look, magnitude can change. In case of linear polarization, magnitude can change. The only concern is the phase difference. Phase difference should be a multiple of n pi. So that means it is linearly polarized only. And what about the lossy case? In lossy case, these guys are having some phase as well. These guys will be having some phase, right? Having phase. This is phi 1, this is phi 2. Having different phase. That means they disturb the phase difference. And if they have disturbed the phase difference, look, this video will always be there on YouTube. And now once you revise this notes, when you will revise this notes, you will be not able to understand anything. Like this is the kind of concept which you need to study again when you are revising. Let's just say you revise this concept after 2 months. Then you will come back and you will read it, you will not understand anything. So at that time when you forget it, you come back to this video. Because in any other institute, this concept is not taught. Okay, I can guarantee it. No one actually teaches this, but certainly it is very important. It can come in the upcoming examination. And from where I have studied it, that also I will tell you. From which resource I have studied this concept. Because from there I have picked up this concept, and that playlist is very important. So that I will tell you later on in this video only. But yeah, as of now I am telling one thing, that if you forget this kind of concept, then you need to come back and then watch it. Okay, again you watch it and again it will come to you. So disturb the phase difference, that means it will become elliptically polarized. Say yes or no, right? Because here the phase difference is disturbed for lossy medium. Now let's take the case of total internal reflection. So in case of total internal reflection, our gamma was already complex. Do you remember this thing? Our gamma was already complex, whether it is for case of gamma parallel or for case of gamma perpendicular. We have seen the case of gamma perpendicular. What was the gamma perpendicular value we were getting? 1 e to the power j, I guess it was 44.41 plus minus. That means it will have some phase as well, and the magnitude will be fixed, that is 1 only. Why is that so? Let's check it with respect to gamma parallel. So neta 2 cos theta I, neta 2 cos theta t minus neta 1 cos theta I divided by neta 2 cos theta t plus neta 1 cos theta I, right? What this will be? Complex. Sorry, not complex. It will be imaginary. Cos theta t will be imaginary. Why is that so? Because sin theta t will be somewhat greater than 1. Let's just say it was under root 2. So when you find out cos theta t, what it was? It has to be imaginary only. So it will be imaginary. So this could be neta into some imaginary value. In our case it was 1, but it can have some imaginary value. Minus neta 1 cos theta I. That will be real. So this is having some real value, that is A. Divided by neta 2 j beta plus neta 1 A. Cos theta t will be real, so A real here I am writing. Sorry, cos theta I will be real, so real I am writing here. Cos theta t would be imaginary, so that's why I am writing imaginary here. What is the magnitude of this quantity? J neta b minus neta 1a divided by j neta 2b plus neta 1a. What will be the magnitude? Under root neta 2b whole square plus neta 1a whole square divided by under root neta 2b whole square. Same, right? So both and both will get cancelled. What is the magnitude? Magnitude is 1, but it will have some phase. This will have some phase difference. So what I mean to say is that your gamma parallel and perpendicular both will have a magnitude of 1, but will have some phase, and both will have different phases, right? both will have different phases. Why is that so? Because formula are different. Here you are applying neta 2 cos theta t. There you will apply neta 2 cos theta I. So formula are different, no? So if formula are different, that means they will have different phases. What about tau? This will also have another phase, but certainly the magnitude will not be 1. Really sorry. It will have some magnitude that I don't care. Let's just say it is having a magnitude of L and this is having a magnitude of M. Any magnitude they will have. If you remember the case, we find out tau perpendicular. So what will be tau perpendicular? That will be 1 plus gamma perpendicular, tau perpendicular. So what is this 1 plus gamma? That is 1 plus 1 e to the power j phi 1. So how will you find 1 plus cos phi 1? 1 plus cos phi 1 plus j sin phi 1. So there is no doubt that this magnitude can never be 1. It could be greater than 1. It could be less than 1. But never it could be equals to 1. So the magnitude will be some L that is not equals to 1. Okay. And it will have some phase as well. Just now we have seen it. It will have some phase as well. This will have some phase as well. So magnitude is some L and it will have some phase. So regarding your total internal reflection, you need to remember these things. Will you be able to remember these things? Say yes or no. The thing is, the reflection coefficient will always have a magnitude of 1 and different phases. And the transmission coefficient will not have a magnitude of 1 and different phases. Say yes or no. And certainly this L will also not be equals to M and it will not be also equals to 1. Now let's write down about the reflected electric field. So in reflected electric field, this is what I'm going to write down. So reflected electric field will have a component of a parallel. So this is your reflected electric field will have a component of a parallel polarization and it will have a component of a perpendicular polarization. For parallel polarization, it is having a magnitude of 1 and a phase of phi 1. It will be multiplied with E0 1. Rest all whatever that is coming, I don't care. Now for perpendicular case, it is having a magnitude of 1 and phase of phi 2. It will be multiplied with E0 2. Rest all whatever that is coming, that I don't care. So previously your phase was 0. Previously we have considered phi is 0. Phi is 0 we have considered. But now the phase is disturbed. Here the phase difference is phi 1 minus phi 2. So your reflected wave, here I can say that phase difference disturbed. That means your reflected wave will be elliptically polarized. Because if the phase difference is not a multiple of n pi or is not a odd multiple of pi by 2, then certainly it will be elliptically polarized. Elliptically polarized. Right? And what about the transmission one? Same goes for transmission one as well. Here, along with the phase, the magnitude is also disturbed. But magnitude was not our matter of concern. Our matter of concern was phase. So along with the phase, magnitude is also disturbed, but that is not our matter of concern. So e to the power j pi. So here let's remove this line, that is of no use. So our transmission coefficient will come for parallel case, that is equals to L into e to the power j pi by 3. It will be multiplied with E naught 1. I don't care about the rest of the things because I only care about the magnitude and the phase. I only care about these two things. In case of linear polarization, in case of circular polarization, I care about the magnitude as well. I care about the phases as well, and I care about the direction of propagation as well. Because in that, if direction of propagation is something different, then left and circularly polarized and right and circularly polarized, that case also will come into action. So that kind of question we will see as well. And what about the perpendicular case? So m into e to the power j pi by 4 e naught 2 and then. So again phase difference disturbed. Along with that, what all things are disturbed? Plus magnitude also disturbed. So transmitted wave will be elliptically polarized. So elliptically polarized here as well, elliptically polarized here also, elliptically polarized, elliptically polarized, elliptically polarized. The only case where you are not getting elliptically polarized is this one. This is your linearly polarized. And just one second, here also you are getting the linearly polarized. So for lossless case, for lossless medium, in case of oblique incidence, for lossless medium, the reflected wave will be linearly polarized if your incident wave is linearly polarized. Are you getting this point? Reflected along with that transmitted wave as well. Here, this is what we are talking about. We are talking about transmitted wave. So here we are talking about transmitted wave. So what we started talking about? We started talking about transmitted wave here. So I hope this is clear to you. Here we were talking about transmitted wave, right? And this was all the talks about reflected wave. Is that clear to you? So don't make any conclusion. You just need to remember the process. That what is the process? Just find out the reflection coefficients, transmission coefficient, and based on that you write down your reflected field and transmitted field, and from there you would get to know that if your phase is getting disturbed, if your magnitude is getting disturbed, then you will realize whether it is circularly polarized, linearly polarized, or elliptically polarized. All okay? Let's get back to the next one. Now your phase difference is an odd multiple of pi by 2, and also it is E naught 1 is equals to E naught 2. That means incident wave is circularly polarized, right? And what we will assume, let phi to be pi by 2. So ordinary reflection, considering the lossless case, and what we will discuss first. First we will discuss about reflected waves. Okay. First we are discussing about reflected waves. So what ordinary reflection and lossless. Ordinary reflection is there, that means no total internal reflection, and it is lossless. That means what will be your gamma parallel? That would be real. And what will be your gamma perpendicular? That will also be real. And what will be your tau parallel? If I am talking about only reflected wave, so I only need gamma perpendicular. Sorry, I only need the value of gamma. So let's drop tau here. But the second thing is, both are never equal. Both are never equal, right? Gamma parallel is never equals to gamma perpendicular. So what will be my reflected field? My reflected field will be, it will be multiplied with gamma parallel E naught 1. Something would be coming here that I don't care. And because what is my incident field that I did not write? Incident field is E naught 1, don't care about that, plus E naught 2 J phi, don't care about that. Here I am not going to discuss right hand circularly polarized, left hand circularly polarized. That thing we are not going to discuss. That thing we will discuss with respect to a question. Okay. As of now, we just need to see from circular polarization to which polarization it is going. Are you getting this point? Left and right hand we will certainly discuss, but with respect to one question. Okay. So as of now, I am not considering the direction of wave propagation. Otherwise, I should have considered the direction of wave propagation as well if I need to see the left hand or right hand circular polarization. Are you getting this point? Okay. So certainly that we will see that thing. Gamma perpendicular E naught 2, the phase is pi by 2. Here I can write phase is pi by 2. And rest of the things I don't care. Here E naught 1 and E naught 2 was equal. This and this was equal. So E naught 1 and E naught 2 was equal. But now this thing and this thing, gamma parallel E naught is not equals to gamma perpendicular E naught. That means phase is not disturbed. Here phase is not disturbed. Phase same. but amplitude changed. So if your amplitude has changed, no matter whether you are having a same phase, like your phase is pi by 2 only, your phase is pi by 2 only here, but amplitude is changed. What does that mean? Elliptically polarized. Say yes or no. Do you agree to this point or not? A very, very good point. That here, in this case, in case of oblique incidence, my gamma perpendicular and gamma parallel will be different. That means they will be added to two same quantities. They are multiplied to E naught and E naught only. Now, effectively, the complete reflected wave will have different magnitude and here also different magnitude. Although the phase is pi by 2 only, but since they are having different magnitude, it will be elliptically polarized only. But now in which direction, left and right hand, that we will certainly see. Don't worry about that. Okay. So here we are talking about reflected wave only. Now let's add a page. I hope you are enjoying this new kind of analysis because I know you haven't seen it anywhere else, right? Yeah. So reflected waves. Now let's talk about transmitted wave for lossless only. Okay. Transmitted wave, we are talking about lossless only. So what about the transmission coefficient? These two transmission coefficient, this will be also real and this will also be real. But the thing is, both will not be equal. So if I write down my transmitted electric field, so what that would be? E naught, don't care. Tau perpendicular, E naught, don't care. Sorry, here phase is also there, no? Rest don't care. If both are real, they are not having the phase. So phase is not disturbed. Phase same. Phase difference same actually. Phase difference same. So here also I should write phase difference same. But amplitude disturbed. That means what is the answer? Elliptically polarized. Let's see for the lossy medium as well. Lossy medium. First we will talk about reflected wave, right? So if I talk about reflected wave first, so in reflected wave, this will have some magnitude, it will have a phase as well. And your transmission coefficient, sorry, reflection coefficient only, it will have a magnitude, it will have a phase as well. That phase will also be difference. So now your both amplitude and phase will be disturbed. From here I can get to know that both amplitude will also be disturbed because gamma parallel and gamma perpendicular both are different, and here phi 1 and phi 2 both are different. So both amplitude and phase difference are disturbed. And what does that mean? Parallel, sorry, what I am writing, elliptically polarized. So left hand or right hand, certainly we will see it in one of the other questions. Now what about the transmitted field, transmitted wave? Same goes for transmitted wave as well. For transmitted wave, this is the scene, right? So here you can directly see that here also the phase and magnitude both are disturbed because both are different here and this is also different. So what will be the answer? Elliptically polarized. Okay. So here you can see that in case of circular polarization, no matter whether it is lossy or lossless, no matter whether it is transmitted or reflected, your circular polarized wave is coming into elliptically polarized only. But this is what they will not ask in the examination, because this is something that you can mug up. That in case of oblique incidence, my circular will be changed to elliptical. This is something that you can mug up. What they will ask in the examination? They will ask right hand circularly polarized, left hand elliptically polarized, left hand circularly polarized, or left hand, right hand, left hand. So these hand they will ask, right? Because here you can see that results are same, whether it is lossy or lossless, results are same only. But in the examination, what they will ask, that kind of question I have already framed. So that we will check out. Don't worry about that. Now, if this is the case of total internal reflection, so this will have a phase, but the magnitude is 1 only. This will also have a phase. Sorry, this will have another amplitude, but phase is also different here, right? So if I write down my reflected wave, so if I write down my reflected wave, what that would be? So your E naught 1 will be multiplied with J phi 1 E naught. Why E naught? Because E naught 1 here is equals to what I have assumed. I have assumed circularly polarized. So E naught 1 is equals to E naught 2 is equals to E naught has been assumed, and phi is taken as pi by 2. So this will be E naught only. The magnitude is 1. This is your reflection coefficient. Reflection coefficient is multiplied with E naught. This I don't care. Plus next my reflection coefficient, that is also 1. That is also multiplied with E naught. It was already having a phase difference of pi by 2. So previously the phase difference was pi by 2. Now what is the phase difference? Now the phase difference is this, pi by 2 plus pi by 2 plus phi 2 minus phi 1. So phase difference is disturbed. That means it is elliptically polarized. Elliptically polarized. Yeah, sorry for the interruption. So where were we? This is elliptically polarized. So here I should have written, no? Because I have already written the reflected wave will be elliptically polarized. Now, do I need to explain this? Do I need to explain this transmitted wave? No. You know that it will be also be elliptically polarized, because phase difference is also changing and here magnitude is also changing. So certainly it will also be elliptically polarized. So here in the all cases, what is the answer that you are getting? That my reflected field is elliptically polarized. But what about right hand, left hand? That is the same. Here also you are getting elliptically polarized. Here also you are getting elliptically polarized. Whether it is a case of total internal reflection, whether you are having lossy medium or you are having lossless medium, your circularly polarized wave is being changed to elliptically polarized only, whether it is reflection or it is transmission. The point is they are changing the magnitude of two perpendicular component. One is the parallel component, one is the perpendicular component. So magnitude is being changed. If the magnitude is disturbed, then certainly they can never be your circularly polarized. But now, one thing I know that the circularly polarized, this question you need to solve on your own. Circularly polarized will become electrically polarized. That I know. But what about right hand, left hand? That you need to think now. So use your all your concept of EMFT, all the concept that you have studied till now, all the concept of EMFT. Use all the concept of EMFT and try this question. These are the three options. You can take the screenshot and one of the option is here. So forget about this option. If you are able to solve the first three options, then you will be able to solve the fourth one as well. So try solving it. Use your all brain. Pause the video and then write down in the comment section whether you solved it correctly or not. Okay, so let's start. First one, what they are saying, a right hand circularly polarized wave is incident on dielectric interface at an angle theta I. For dielectric 1 having incident and reflected wave, the intrinsic impedance is neta 1, and for dielectric 2, the intrinsic impedance is neta 2. Consider theta t as the transmitted angle. Find the correct statement. So can I make a right hand circularly polarized wave which is incident at an angle theta I? That means it is the case of oblique incidence. So can I make any wave like that? What I need to make, this is the boundary plane. This is my boundary plane and this is my plane of incidence, and this is how my wave is coming. My wave is coming like this, and it is striking at an angle of theta I. What I need to make? I need to make a circularly right hand circularly polarized wave. What I need to make? Right hand circularly polarized incident wave I need to make. So polarization is always defined with respect to E field. Polarization is always defined with respect to E field. So what I need to do? Let's just say one component of E field I consider in this direction, and the other component of E field I am considering in this direction, and this is my direction of propagation. Okay, this is my direction of propagation. So this is the parallel component I am considering, and this is the perpendicular component I am considering. If I consider this component, so this perpendicular component, this is the parallel component and this is the perpendicular component, and this is phase shifted by pi by 2. This is what I am considering. So this perpendicular component is going inside. Are you able to understand? This perpendicular component is going inside. So this is having a, let's just say I keep it minus pi by 2. That means this is leading. This is leading. And the component that is inside, that is lagging. So if I use my right hand, lead to lag, then my thumb should be in the direction of propagation. Are you getting to know what I am doing? There would be two components. One will be the parallel, another one will be the perpendicular. So parallel component I assumed and perpendicular component I assumed. Blindly I have assumed it. Blindly, without even thinking anything. Without even thinking anything, I assumed two components. One thing I am pretty sure that my parallel component could be either this or this, and my perpendicular component could be either inside or outside. So blindly I assumed two components. Say yes or no. Now what I need to do? I need to move my hand from lead to lag. And what I need to move? I need to move my right hand. If I move my hand from lead to lag, my thumb should show the direction of wave propagation. Now which is my leading? If I call this as minus pi by 2. So this is leading and this is lagging. So inside the plane lagging, and if in the plane leading. So lead to lag, thumb is showing towards the direction of propagation. No, it is showing opposite to the direction of propagation. So what I can change? What I can change is that one thing I can do is that this I can make. Or what I could have done, I could have, if I want to keep it like this, then I could have changed to this. What I mean to say is that the component that is inside, that is leading. The component that is inside, that is leading. So from lead to lag, I need to use my hand. So lead to lag, if I am using my hand, my direction of propagation is this one. You need to visualize it. I hope I have given enough visualization. If I have made like this, that means the component that is inside, that would be leading, and this would be lagging. So you need to take your hand from lead to lag, and thumb should show the direction of wave propagation. Yes, with the right hand I am able to achieve it. So this is the wave that I wanted. There you go. Or what I could have done? What I could have done is that this and this thing. Now you let me know whether it is right hand circularly polarized or not. This is your lead. Now this is your lead. And where is your lag? Lag is coming towards you. So from lead to lag, lag is coming towards you. From lead to lag, and thumb should show the direction of wave propagation. Yes, this is also right hand circularly polarized. So any kind of wave you can assume. There are different kind of right hand circularly polarized wave I can make. I am choosing this one now. As of now, I am choosing this one. Are you able to understand this point? That how we are making circularly polarized wave here, right hand circularly polarized. Now let's take the first case. In the first case, what they are saying. Yeah, now let's make the respective diagram as well. Which respective diagram we are talking about? Reflected and transmitted. Okay. Now we have derived the formula with respect to what? With respect to our assumption. What is the assumption? If this is the perpendicular component of incident field, so this will be the perpendicular component of incident field, because reflected field, because electric field never changes its direction. This is what we assume. So perpendicular component and transmitted component all are in the same direction. This is what we assume. Incident, transmitted and reflected all are in the same direction. Now if this is your incident electric field, then what is your reflected electric field? This is your reflected electric field. And this is your transmitted electric field. So now whatever the formula we have derived with respect to this setup. So always this setup should be clear in your mind. That for parallel polarization, what kind of setup I have assumed, and for perpendicular polarization, what kind of setup I have assumed. So in perpendicular polarization, again I am repeating it. I guess in the lecture series itself, I have said this thing more than 20 times. That for perpendicular polarization, we have assumed that electric field never changes its direction, and for parallel polarization, we have assumed that magnetic field changes its direction. So if magnetic field is changing its direction, then with respect to this field, I can find the direction of magnetic field. Then from here to here, I will change the direction of magnetic field. And if I know the direction of magnetic field here, I can find the direction of electric field. But till now, we have solved this question again and again. So I know that this will be my reflected electric field, right? So how I am getting it, that we already know, right? E cross H. So this will be the direction. And now both of them have the same orientation. Both of them have the same orientation. So this is how the orientation will be looking like for incident and transmitted. So this is the this is something that we have studied. And for them, for this particular condition, we have derived two formula: neta 2 cos theta t minus neta 1 cos theta I divided by neta 2 cos theta t plus neta 1 cos theta I. And for perpendicular, neta 2 cos theta I minus neta 1 cos theta t divided by neta 2 cos theta I plus neta 1 cos theta t. Well and good. Let's take up the cases now. First case. Okay, I have the page. Now what we are saying in the first option. In the first option, they are saying that neta 2 cos theta t is greater than neta 1 cos theta I, and neta 2 cos theta I is greater than neta 1 cos theta t. That means this guy is greater than this one, and this guy is greater than this one. What does that mean? That your gamma perpendicular, your gamma parallel is positive, and your gamma perpendicular is positive. Certainly, we already know that both can never be equal. Are you getting this point? Both will never be equal, that I already know, but both are positive. Both are positive means this diagram remains correct. That means in our assumption, if we get the gamma parallel and perpendicular to be positive, that means now I don't need to change any direction. That means for my reflected field, if I draw my reflected field, then my reflected field will be like this. This is my direction of wave propagation. This is the parallel component, which is like this. And this is my perpendicular component. What I am saying, are you getting this point or not? If you have studied oblique incidence in a good manner, then only you will be able to understand what I am saying. What I am saying, that if both are coming positive, that means whatever the actual direction we are having, that is correct only. Because we assumed this phenomena and then we derived this formula. If I had assumed some other phenomena, if I assumed some other direction, then the formula would be different. So usually when we study oblique incidence, what people do is that they remember the formula, but they don't remember the setup. Remembering setup is also very important. If you remember the setup, then gamma parallel positive, gamma perpendicular positive, there will be no issue in that. Okay, so this is the direction of your reflected electric field. Now let me know whether it is and there is no phase difference. What I mean to say is that phase difference is not disturbed. Phase difference is not disturbed. Phase difference is not disturbed, but what is disturbed? Magnitude is disturbed. Magnitude is disturbed. And what does that mean? It is elliptically polarized. But left hand or right hand? For that, what I need to do? I need to use my hands. So, which is lead, which is lag? If phase is not disturbed, that means here, this was your lead. Your parallel component was lead. And if phase is not disturbed, then what will happen? If I write down the reflected electric field, total reflected electric field, if I write down. So what I will write down? Gamma parallel, E naught. This was already having a phase of pi by 2. Rest thing I don't care. Plus gamma perpendicular E naught, this was not having any phase. So here this was lead. Previously this was again lead. Now also this is also lead. Here also it is lead only. In the previous case, this was the lead. Here this was the lead. Here this is the lead. I can say it. Now if the phase is not getting changed, that means this phase is not disturbed. So again this is the lead only. He is the lead and he is the lag. This guy is the lead and this guy is the lag. So from where to where I need to use my hand? I need to use my from lead to lag. Lag is coming towards me, sorry. Lead to lag. So thumb should show the direction of propagation. No, right hand is not showing. So I need to use the left hand. From lead to lag. Lead to lag. Thumb should show the direction of propagation. Yes, that means it is left hand elliptically polarized. Look, a very, very deep concept. Like if this question comes in the examination, then I guess one or two guys will be able to solve it if they haven't studied the concept. Hardly one or two guys I am saying it. And that is also not sure. Okay. So this kind of deep concept we are studying here. What we are studying, the reflected wave, we saw it. Incident wave was right hand circularly polarized. So I need to assume any right hand circularly polarized. Now what you can do, you can assume something else. Assume something else right hand circularly polarized wave and then do the same analysis. You will get the same answer only. What I mean to say is that what I could have done is that this is my E parallel incident and E perpendicular incident I could have taken inside the plane and then I could have given it a phase of plus pi by 2, right? Or minus pi by 2. You can take whatever it is. If I take it plus pi by 2, so lead to lag. Minus pi by 2 I need to give, right? Lead to lag. Lead to lag. No, plus pi by 2, sorry. Yeah, plus pi by 2. Yeah. So if I take this scenario as well, then also this wave is right hand circularly polarized. Then you do the same analysis for gamma equals to positive and gamma perpendicular equals to positive and gamma parallel equals to positive. You will get the same answer. Okay. So this analysis I am keeping up to you. But first I randomly choose any right hand circularly polarized wave. Then I got to know that phase is not getting changed. Here phase difference will not be disturbed. Why is that so? Because here gamma parallel and gamma perpendicular will be real. And if they are real, that means this parallel component was in lead. Now this will be in lead only. And this perpendicular component was in lag. This will be in lag only. And what is the setup that we have assumed? The setup that we have assumed is that if this is my parallel, then this would be my parallel. And if this is my perpendicular, then perpendicular direction will not change. So this is the setup we have assumed for these formulas. And for the given condition, I got to know if I put the given condition in this formula, I get to know that these I am getting as positive. That means my reflected electric field is not changing in direction, neither for parallel, neither for perpendicular. So my reflected electric field, now if they are not changing the direction, so from right hand circularly polarized to, we are getting left hand elliptically polarized. Let's take the second case. In second case, what they are saying, neta 2 cos theta t is lesser than neta 1 cos theta I. Neta 2 cos theta t is lesser than neta 1 cos theta I and neta 2 cos theta I is lesser than neta 1 cos theta t. Neta 2 cos theta I is lesser than neta 1 cos theta t and neta 2 cos theta I t is lesser than neta 1 cos theta I. That means both are negative. And what does that mean? Both are negative, certainly, though they are not equal. That's for sure, because formula are different. So again, phase difference is not disturbed. So whoever that was in lead, that will be in lead only. Whoever that was in lag, that will be in lag only. Phase difference not disturbed. But what is the scene? But magnitude is disturbed. That means certainly it is elliptically polarized, but I need to check the hand now, right hand or left hand. Now people say that I am a young educator and I cannot teach. Now I challenge them that in gate industry, if anyone can teach this concept. Okay, I should not be arrogant, but I have been receiving the comments from some educators now. So that is something like something disheartening for me, that they say that I am a young student and I am a student who is teaching. Like who teaches these concepts then? Okay, it takes a lot of effort to bring these kind of questions. I can bring easy questions, I can bring easy PYQs, but why don't I do this thing? Why I'm bringing FIQ? Because that will take effort, no? Right? That will take a lot of effort. There, like actual things will be taught there. But forget about this thing. Let's not talk about it. So, gamma parallel is negative and gamma perpendicular is negative. What does that mean? Both will change the direction. And now, like everyone teaches parallel polarization, everyone teaches this perpendicular polarization. No one teaches that you need to remember the setup as well. They derive the formula, but they never say that we are deriving it for a particular setup. That's why that gate PYQ that was asked previously in 2013, that is still solved wrong. Because we never remember the setup. But we are deriving all these formula with respect to one setup. I'm not like disrespecting anyone, not defaming anyone, but like if I am respecting them, then they can also respect back. This is what something I am saying. Okay. So yeah. So here, what was our assumption? That parallel component is never changing its direction. Sorry, perpendicular component is never changing its direction. But if you are getting gamma perpendicular to be negative, that means your in reflected wave, it will change the direction. We have assumed it to be coming towards us, but since the gamma perpendicular is negative, it is going inside the plane. And here we have assumed parallel component to be in this direction. The parallel component could be either here or it could be here. We have assumed to be in this direction, but since the gamma parallel is becoming negative, then actually it would have been somewhere here. So this is your parallel component of reflected field, and this is your perpendicular component of reflected field. Now which hand you need to use? Again, I guess we need to use the left hand, right? Because if I use the left hand going inside, yes, thumb should show the direction of propagation. You can see it, we need to use left hand. This goes here. Yeah, which one is in lead? This is in lead only, no? Because here the magnitude is only changing, phase is not disturbed. So previously this was in lead, here also this is in lead only. It will always be in lead. This will be lag only. Because here magnitude is disturbed, but the phase is not disturbed. Because they are not even having a phase. You can say, sir, they are having the phase of pi. You can say that, sir, they are having the phase of pi. Yes, they are having the phase of pi, but both are having the same phase, no? This guy, perpendicular guy will also have the same phase, parallel guy will also have the same phase. So if both are having the same phase, that means that part will be cut, and again pi by 2 phase will be there. And I have assumed the parallel component to be in lead, so here also that is in lead. So from lead to lag, and the direction, and should show the direction of wave propagation. There you go. So left hand elliptically polarized. Let's take the case C. Which case? Case C. Okay. So in case C, what they are saying, neta 2 cos theta t is greater than neta 1 cos theta I. That means gamma parallel is positive and gamma perpendicular is negative, because this is negative. So you can directly see here, this is positive and this is negative. So this is what they are saying. So gamma parallel is positive and gamma perpendicular is negative. So we are not going to write down these things again and again. I know that phase difference is not disturbed, magnitude is disturbed, so certainly it will be elliptically polarized. Now just need to see left hand or right hand. So this is my direction of wave propagation. Who is changing? Gamma perpendicular. Gamma perpendicular is negative. That means this we are assuming coming towards us, but actually it is going down. Actually it is going down. This is the perpendicular component. And what about the parallel component? Parallel component remains there only. Parallel component remains there only. Because parallel component is having positive value. Parallel component is having positive value. That means our assumption was correct. We assumed the parallel component of E field to be in this direction. That is in this direction only. Okay. So which is in lead? This is in lead. And which is in lag? Lag is going inside. So from lead to lag, which hand I need to use? Right hand. Elliptically polarized. Okay. So first option, second option, third option, all are correct. You can check the last one as well. This will also be correct. Okay, do it on your own. At least this should be done on your own. Yeah. Right? Here, what is the scene? This is negative and this is positive. Okay, so both are changing the direction. No, sorry, not both are changing the direction. Here perpendicular is positive, so this is coming towards me only, but this guy is changing the direction. This guy is coming here. Now who is in lead? Who is in lead? This guy is in lead. And who is in lag? This guy is in lag. So from lead to lag. But which hand I need to use? ये क्या हो गया? Okay, sorry, yeah. Lead to lag. Lag. It is coming towards me. Lead to lag. So right hand elliptically polarized. Yes or no? Right? One final concept is left now. This is the one final question. You can call it as a concept as well. You can call it as a question as well. Try thinking about it. An elliptically polarized EM wave is incident at an angle of theta I on a dielectric interface. For dielectric 1, having the dielectric 1 means for medium 1. For medium 1, epsilon R1 mu R1 is given. For medium 2, epsilon R2 mu R2 is given. What should be the value of theta I such that reflected wave is linearly polarized? From elliptically polarized, you need linearly polarized wave. What you can do? Think about it, think about it. Put pressure on your brain. Put pressure on your brain. Even if you are not able to solve it, then also it is fine. But I'm pretty sure in next 2 to 3 years, these kind of questions are coming. They are never introduced. Now I will tell you from where the questions are framed, how the questions could be coming. So everything will come in this video only, in the next part of this video. Okay, certainly these kind of questions are coming. Yeah, so what I was saying, this is your elliptically polarized wave. Can you make any elliptically polarized wave? Yes. Basically, it will have a parallel component. It will have a parallel component and it will have a perpendicular component. Right. Now both are, let's just say both are having the same magnitude. Parallel component is also having the same magnitude. What I mean to say is that I am writing my incident field. Okay. So I am assuming this is having a magnitude of E01. Rest all I am not writing, and it is having a phase of 0. It is having a phase of 0 that I am writing down. So whatever it is coming, that I don't care now. Now this is the perpendicular component. This is the parallel component, no? So how I can write the parallel component, how I was writing it? Okay, I was not even writing it. Just 1 second. How will I write the parallel component? How I have written the parallel component here? Okay, in the same manner only. So here I am writing E0 parallel and E0 perpendicular. I am assuming both are having the same magnitude, or it could be different as well. But if I make a random phase between them, like if there is a random phase difference between them, then which kind of wave it will be? Elliptically polarized, right? Say yes or no. If there is a random phase difference, it is not pi by 2, it is neither pi. These magnitude could be equal. If I make a random phase difference, that means it is elliptically polarized. Now what do I need? I need what do I need? I need my wave to be linearly polarized. I am giving you a hint. Hint is Brewster angle. It should be clear now. Because if your wave is incident at Brewster angle, if your wave is here, mu r1 is equals to mu r2, mu r1 is equals to mu r2. So here Brewster angle for perpendicular polarization is not defined. Say yes or no. Because if both are equal, mu r1 and mu r2 is equal, then for Brewster angle for perpendicular polarization is not defined. So which Brewster angle is defined? For parallel polarization. So if your wave is incident at the Brewster angle, then what will happen? Then my reflected wave will not have any parallel component. Right? What we study? If my wave is incident on Brewster angle, that means reflected wave will not, there will be no reflected wave. This is what we study. What we study is that if your wave is incident at the Brewster angle, then there will be no reflected wave. The complete wave will be transmitted. But here there are two components. Parallel component is also there and perpendicular component is also there. So in your reflected wave, what you will have? Only one component, that is perpendicular. So if theta I is equals to theta b parallel, then no parallel reflected wave. That means your E transmitted will have only perpendicular component, only perpendicular component, only one component I can say. So it will have that component which is your gamma perpendicular would be there. It can have some phase as well, I don't care. Then it was having a phase of e to the power j pi by 3. That phase is also there, and E naught 1. So if only one component is there, that means certainly it is linearly polarized. Are you getting this point? If you remember the example here, right in the beginning as well, we saw this example. Which example? Here. That if only one component is there, that means certainly it has to be linearly polarized. So I just killed the other part. Which part? I killed the other part using the Brewster angle, because if I am putting it at Brewster angle, that means the other part will be killed. Which other part? The parallel part will be killed. So only one part will be left. So that's why it is linearly polarized. So what is my Brewster angle? If you remember the formula, tan inverse under root epsilon r2 divided by under root epsilon r1. So tan inverse under root epsilon r2 is, so this will be under root 2 by 3. So tan Brewster angle will be equals to what? I can do the calculation. So ये तो क्या गया यार, 2/3 under root tan inverse 39.23. Okay. So with great visualization, with great 90 hours, I hope you enjoyed the lecture. I hope you have fallen in love with the subject or with the educator. No, why would you fall in love with the educator? I hope you would have fallen in love with the teaching style, or I hope you would have fallen in love with the subject as well. And I hope you are confident enough with this particular subject. So this is the complete 90 hours of marathon with decent health. I was not up to my 100% health. I don't know when I will be at 100% health, but with decent health and I guess good enough explanation. I have given my every single effort, whatever that I could have done in this particular playlist that is there on our YouTube channel itself. That is for EMFT. So I hope you would have enjoyed studying EMFT from me. And even if you have already studied, I guess you would have studied a lot of new concepts, right? Okay, so now you should be knowing that what all we have covered. So this is the playlist which we have covered almost 90%, whatever that is there in the syllabus. So this is the playlist by Shivgankar sir, a brilliant playlist, awesome playlist, and even the explanation is also very good. So if you want to follow this playlist after gate examination, you can follow it. Already 90% of the things you will be already knowing. You will build up your concept only. So if you want to follow it, you can follow it. But after the gate examination, since you have already covered this particular lecture series, then as of now you don't need to follow it. So this has been covered. Now let's take the book one by one. And why not 100%? Because this is, some things are not in our syllabus, so that we have dropped. Now let's take the book one by one. So first one, Sadiku, which book we usually follow. So this is the book we are following. First one, that is the Sadiku. So in Sadiku, what all we have covered? This cover chapter completely, coordinate system as well, vector calculus as well, and mostly all the solved unsolved example we have seen, right? Now we have dropped chapter 4 to 8 for EC student. For electrical student, we have covered 4 to 8 as well. But for EC student, we have dropped it. For this is in the syllabus of electrical. So that's why we have dropped 4 to 8. Only the surface level part we have studied. Then we started with Maxwell equation, EM wave, transmission line, we have covered completely. Now in waveguide, we did not study resonators because it is not specifically mentioned in your syllabus. But sometimes, like until this date, never the question has been asked on resonators. But if I feel like that I need to teach it, then someday I can teach it as well. Now you would be thinking, sir, that what is this, sir, waveguide, current and mode excitation? This is just field pattern. We saw the field pattern, no? So all these things we have seen. And here only rectangular waveguide is there. We have studied circular waveguide as well, right? So this completely we have seen, and this also completely we have seen. This radar we haven't seen because this has been removed from your syllabus. In some other playlist you can find some concept on radar. Even in the test series as well you can find some concept of radar, but certainly it will not come. Okay, you don't need to worry, it will not come in your examination. So the radar we do not study, right? Let's come to the second book, that is Cheng. This book, field and wave electromagnetics. So this, in this book we have covered the vector analysis part. Mainly from this book we have studied transmission line, because this is one of the finest book for transmission line. But whatever that is there here as well for time varying field, that also we have covered. I guess I have put the slide on next page as well. Yeah, so for time varying fields we did not cover EMI in great depth, like Faraday's law for electromagnetic induction. Whatever that was required, that we covered, but we did not see any numerical, right? We have covered Faraday's law, but on surface level, whatever that is required, we did not see any numerical on that. So that we have covered. Then Maxwell equation completely we have covered. Potential function is also kind of we have seen it, E is equals to minus delta V. Then magnetic vector potential also we saw in antenna as well. Then boundary condition we have seen. Then EM wave equation, their derivation for time harmonic vector field as well, we have seen it, right? And then these are the properties of wave, like in lossy medium, lossless medium. So all these points we have seen: normal incidence, oblique incidence, and in whatever the concept that we have studied in last two videos, the total internal reflection, and this is the polarization. So that is not mentioned in any of the books. That I copied from here, that I studied from here. Okay, I should not say copied. Like if someone is thinking I am copying it, then I don't. I cannot say anything else. But this is something that I studied from here. But the content that I am delivering here, that is something different only. Like these questions I framed on my own only. The statement wise question has been framed on my own. This question is also framed on my own, right? And all these complete concept is framed on my own only. But from here you would get a basic idea. They explained this concept in roughly around 20 to 30 minutes. But we are spending more than 2.5 hours. So this is the thing, like in NPTEL, educator can study. But for a student, we need to elaborate it. So that we have done here, right? Now this part, then this is the plane wave. And here, I guess on the next page as well, I have put it for transmission line. Yeah. So for transmission line, this book is very, very good. So all these concepts we have seen. Now coming to this part, transient. In transient, we did not see the initially charged line. Like on the transmission line, I never gave any initial charge, and load that I connected was always resistive. So we did not see it for reactive load, like for capacitive and inductive load. So these 2 points also we did not cover, although like they did not even ask the question on pulse excitation yet. But in the upcoming examination, the question could be coming on pulse excitation as well. So as of now, we did not cover it, but who knows, it can be asked in the examination. So later on, I can cover it. But these are like very, very rare important. Okay. So as of now, what 2 topics we can see? Waveguide, resonator, and these 2 topics. Okay. But these are like very, very rarely important. That's like they are never asked, never ever asked. So that's why we did not cover it. Now, wave polarization have been asked a lot of time. So that's why we saw this concept. This is the concept of wave polarization only, what we have seen here, right? Yeah, so Smith chart we have covered completely only. And in Smith chart, the single step matching we did not cover, because from here numerical is very difficult. Like there is very rare chance that numerical can be framed. And whatever the numerical that can be framed from single step matching, that we have already seen. We have seen what is the meaning of step matching, but we did not see it with respect to the Smith chart. So with respect to Smith chart as well, single step matching can be studied. So if someday I feel like that I need to make a video, then I can make a video. But till now, there is no questions has been framed on this. And what I feel is that in future as well, there might be very less questions. Rest all things we have already covered. And from waveguide, these things we have covered. So rectangular we have covered, circular we have covered, general introduction, all these things we have covered. Now, you would say that, sir, parallel plate waveguide, not mentioned in the syllabus, but in the previous year questions, some question has come. So that also we have seen, that how to solve the questions of parallel plate waveguide using the concept of rectangular waveguide. Have we seen this? Certainly we have seen this, that how to solve the parallel plate waveguide using rectangular waveguide. So we solved 2 questions there, where I took the length to be infinity. So that we saw it, right? And this dielectric waveguide and cavity, this is not even in the syllabus. And resonator we did not cover it, that I am already saying. So resonator as of now we did not cover, but if it is required, like I don't think it is required, because no one covers it, and neither in this playlist resonators are covered. In which playlist? In which playlist? If we take this as a reference, resonators are not covered. Okay, so that's why we are dropping it. So resonators we are dropping it. And now coming to this waveguide that we have already seen. Now antennas, just there are some other type of antenna we did not see, like Yagi-Uda antenna, helical antenna, broadband antenna. These are not in the syllabus. So these type of antenna we did not see. Rest all topics have been covered. Now coming to the Balanese for your antenna part. So only the surface level 1, 2, 3, 4, 6 we have seen. I am not saying that complete chapter we have seen. This Balanese is the book only for antenna part only. This is the book for only antenna theory. So only the required part we have seen. I am not saying completely we have seen it. Whatever the radiation pattern is given in the book, all those radiation pattern we have seen, like whatever the analysis for linear dipole antenna, for Hertzian dipole antenna is given, that also we have seen, right? For antenna array as well, broadside array and fire array, all those concept also we have seen. So whatever that is required, that we have seen from this book, Antenna Theory, Analysis and Design by Balanese sir. Okay, so yeah, that's it from my side. Thank you very much. If I have anything else to deliver, no. All the notes is uploaded on Telegram group. I will upload it in the app as well. Like in the app, you will see the course is of some price. The price would be there. I guess it would be somewhat around 499. So that price is for the test series and for the doubt solving. Okay. If you want to watch the videos, these are available on YouTube itself. So this price is, if you want doubt solving from my side in the Telegram group, then you will get it. If you want test series from my side, which I will be designing, and some questions I will be getting from some gate ranker. So if you want these things, then you can pay it. Otherwise, for video lectures, completely, absolutely available, absolutely freely available on YouTube. Well and good. Thank you very much. Thank you for having me. It's been a great journey. Thank you very much.